Hi everyone, myself Venkatesh, and my topic for today's video is about dearrangement. So let's get started. So let's get into introduction part. So what exactly is dearrangements? In discrete mathematics, a dearrangement is a special kind of permutation where no element appears in its original position. Suppose you have a set of n distinct elements. A dearrangement of a set is a set that permutation such that for every element, its new position is different from its original position. Such that its concept is particularly important in combinatorics. There is a branch of discrete mathematics concerned with the counting and arrangements. Now we shall look at the formula of the dearrangement. Suppose there is an element such as dn that denotes the number of dearrangements of n objects. The general formula is as shown. So this particular formula is derived from the inclusion-exclusion principle, where we subtract the number of permutation with at least one fixed point. Now we shall look at the applications of dearrangements one by one. So first is the secret Santa game, where no one should get their own name, such as a classic use of dearrangements. Next is a puzzle design, where it is like a game like of add check problem. Next is the cryptography, where there is a random shuffling without any fixed point. Next is the coding theory, where there is random arrangements in hashing and coding. At last, it is error detection, where it identifies the invalid mappings in a system. So why does the dearrangement actually matter? So the dearrangement controls the randomness. They allow randomness with constraints. The dearrangement is a study of permutations such that it helps to understand the complex permutation with behaviors. The dearrangement helps in efficiency of the algorithms. In many algorithms, dearrangement structures avoid unnecessary computations or cycles. So we shall look at an example of dearrangements where we consider the n as 3 and all the permutations of n number of objects is 1, 2, 3. So we can see here that 1, 2, 3 is not a dearrangement and 1 is in a place that is not a dearrangement and 3 is in a place that is not a dearrangement. So at 4 we can see 2, 3, 1 and 3, 1, 2 is in a dearrangement place. So at last we can confirm that 2, 3, 1 and 3, 1, 2. So there are two number of dearrangement in this particular example. So we can look at an example which I've explained in a previous slide. So in conclusion, dearrangement demonstrate how constraints in permutations lead to beautiful mathematical structures. They challenge our intuitive sense of order and are excellent examples of how combinatorics uses algebraic tools, how mathematical theory connects with real-world system, how a simple restriction leads to deep consequences in probability and design. Thank you.